Oh, what happened now?
To the 10th stage, then come to ground. First step.
Yeah. Should I wear that? I guess so. Very good. I will wear that. So butterfly hysteresis. Whom of you can tell me what are the two parameters we need to identify from the butterfly hysteresis? So in the end, we can use our piezo ceramic. There are two specific parameters we need. What are those?
Maximum electric field.
Maximum electric field?
Strain.
Sorry?
Strain.
Strain or displacement? Yes, but this is there a specific value for that? No. Okay. Then another value maybe we could find. Electric field, sorry? That's the one. That's a very important one. So if we know to the one hand side, if we know to the one side the maximum electric field strength we can use, and to the other side the negative coercive field strength, then we know the range in which our piezo can work. And since this is the basically maximum range of the piezo, we need to shorten the use range a little bit. Do you remember what are the values? How do I get the operating range from the coercive field strength and the maximum field? Can you remember?
Upper limit is maximum electric field by half.
Exactly, half by half. And coercive? One third coercive. And then you have the operating range. So it makes a lot of sense to know these two things. The only problem is the maximum field strength. If we want to determine that experimentally, then it very well happened that we damaged the piezo ceramic. Because do you know what happened when we exceed the maximum field strength?
Maximum displacement will not change.
Okay.
And the sensor may damage.
Sorry?
Sensor may damage.
Why?
Because its limit.
Why? Ideas. Why does the piezo ceramic? Sorry? If you exceed the maximum field strength? No, I don't think so. No, that happens if you go above the temperature.
Electric breakdown.
What is a breakdown?
Above the maximum voltage, you apply more voltage.
Then what happens? What is a sudden breakdown? Can you describe it a little bit better? Sorry?
Strains will come in material and material will not recover its original shape.
Not quite.
It's like avalanche effect.
Okay, so what you have in a piezoelectric is you have an electrode and a second electrode and you put a field in between, an electric field. And if you have a thunderstorm and you have two electric fields, what happens?
Discharge.
Decharge. Okay, spontaneous decharge. And how do you call that?
Short circuit.
Flash. Flash. It's a flash. You will get a flash. So as in a piezo lighter, you know, a lighter where you push and you get it. The same thing will happen to the piezo ceramic, and then you have a short circuited it, and then there's no current, then there's no voltage anymore because it can just flow away. So the piezoelectric itself is a dielectric, you know, like air has a very low dielectric field, but then a piezoelectric is a ceramic, it has a high one. But if you go above that, you will get a flash and you will get a short circuit through your piezoelectric. And then what you can do, if you ever do that, in patch actuators, as we have them here, for example, you will see black dots where that happens. Of course, you have a flash, it burns. You will see black dots, and then you can drill through them. You drill basically through the whole ceramic. You can put some resin or glue inside, and then it's repaired. So then it works. That only works for such D31 patch actuators. It's a little bit more difficult if you have interdigital electrodes. Then you have to really look what you're doing, because you can also then completely destroy them. Anyway, this is what happens if you go above maximum. And since we don't want to do that, we stick to the data sheet. The data sheet says 120 volts. And I have my own safety, so we say 100 volts. But then we're still way above coercive field strength. So what we will now do to get the butterfly hysteresis is we will not, as described in the lab, we will not do it point by point with DC voltage and then collect a few 20, 30 points, because then we will be here until late evening. We will do it as we did it in the lecture at once, and we will take a very low frequency sine for the voltage. So the voltage goes up, down to the negative, up, down, and then at the same time the displacement changes accordingly, and we should be able to see the butterfly. And once we see the butterfly, we can press the run stop button on the oscilloscope, and then we can use the cursor to look where is the coercive field strength, or better, where is the voltage, the input voltage. Then we have to amplify it with the amplification factor, and then we have to divide it by the electron distance, which is 0.056 mm. And then we have the field strength we are actually applying to the piezo stack actuator, and then we have the coercive field strength. And the maximum field strength is easy. Here we only have to apply the voltage of 100 volts and divide that by 0.056. And then, as you know, it should be something like 1.6 kilovolts or something per millimeter.
So 0.056 is?
Oh, it's the electrode distance. So the stack actuator is, can you see that? I guess you can. So if you have a closer look at the stack actuator has electrodes from this side and electrodes from this side, which are connected. And now to both of these streams of electrodes, you have one electrode like this, but it won't touch that one. And then you have one like this, and one like this, and one like this. So you apply a field here, 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 here. And it's always a field like this, a field like this, a field like this, and always in between there's the piezo ceramic. And the distance between two of these neighboring electrodes is 0.056 mm. So this is the distance you need to calculate your field strength from your voltage. Okay?
By D.
I didn't get that.
By changing V, D are keeping constant. By changing V, you are changing the electric voltage.
So the voltage, yeah. Okay, and I now, when you were in the lecture, I tried to find good settings for a nice butterfly hysteresis. Remember, we have only displacements of the actuator of around 20-40 micrometers, and the voltage, the input voltage of the generator should be between negative 100 volts and plus 100 volts, so 500 millivolts plus minus. So the scale needs to be good. Otherwise, if the scale is really deformed, then you won't see a butterfly, you will just see a line. So your task now is try to set everything up, but before you activate the amplifier, please let me have a look. Okay? Good. Same groups as this morning, one group here, one group there, and go for it. And if you have any questions, obviously. So this one indicates always where your signal is.
Okay.
I suggest to get the laser, to set the laser distance to something around 200 millivolt. So that would be 0.2 mm. So right now it should go down, I think. No, not the screw. Yeah. If you didn't change, that should be sufficient. Oh, you're out of range. Yeah, okay, that was good. You've zoomed into millivolts, yeah?
50 millivolts.
Can you explain what? Okay. Okay, yeah, sure. So what's your idea?
First of all, we set the voltage.
You're out of range. See that it blinks red and green, and now you're in range. So it was, I don't know, maybe it was me, like putting something at the table. At how many? You're almost at 0. Try to get it up to 1. Can you zoom in a little bit?
Zoom.
Oh yeah, millivolts, very good. Zoom in more. Push the button once and then try again. Now very careful.
This button.
Yeah, the one you were just turning at. And now. Okay, let's see. Okay. Can you see that?
Yeah.
You know what happens there? When I do this? It is out of range. As soon as I make only this, it's out of range. This is because it's very close to 0. Let's have another look. So we're at 510, 1 volt, 500, 200. Aha. Okay. And let's put it down a little bit. So now we're at 20 millivolts. Let's make that 100 millivolts. No, that was the wrong way around. Oh, that didn't work. Minus 100 millivolts.
This scale, you have to also change.
Okay, so this is already inverted and it's at 100 millivolts. That's fine. So this is fine. Now you need to activate, first of all, the function generator. Do you know how you do that? Does someone know? No, that's, yeah, okay, good idea. Yeah? So if someone has an idea, maybe you discuss first.
This one, sir? G1.
G1 could be function generator 1. Try that.
And
Okay, and now you see G1, the light hit on. And you can also see that. And now I put out the time scale a little bit. And always when someone touches the table, it goes like this. So I can see it here. If someone touches the table, I see it because we lose the signal. Okay, we're still sometimes losing the signal. Okay, can you tell me what frequency has the function generator and what amplitude?
1 volt amplitude and frequency 100 megahertz.
Mm-hmm.
Yes.
Sorry again, 500 millihertz. So
100.
100 millihertz, so 0.1 hertz.
Yeah.
That's good.
Now we kept the 55 volt.
Your laser distance sensor is not orthogonal to the stack actuator. Exactly. And where are you now? You're still a little bit too low. Try to get that up to 100.
millivolts.
Let me see. So now, right now, you're at 38. Try to get that up with that wheel to 100. Very, very careful.
कम हो रहा है थोड़ा ऊपर ही चार्जिंग करो लगे कम हो रहा है माइनस में हो गया रेड हो गया थोड़ा सा आउट ऑफ एंटी क्लॉकवाइज किया था मैंने क्लॉकवाइज से ऊपर आएगा तो आ रहा है और चाहिए ऊपर आ गया वो नीचे जाएगा
You can actually read the value it just has here, right?
Yeah.
And you should get it to 100 to 100 millivolts. So you're getting in the right direction? Yes?
So now it is 55 volt after amplification.
After amplification.
Not amplified, but before that. After. If you amplify, you get 55 volt.
Okay, so the generator
Yes.
or the laser distance sensor?
No.
Laser distance.
Yes.
Okay, so where's the laser distance sensor now? At how much millivolts?
225.96 millivolt.
225.96.
Yes.
Okay, 225.
This is 200 amplification.
Yes, but you don't amplify the signal of the laser distance sensor. This is just the distance. Okay? Yeah. Okay, good. Can you try to get it close to 200?
Yes.
Do that. Is it inverted or not?
It is not just like a voltage is again increasing.
Sorry, what is increasing?
Like when we decrease the distance up to certain level, there was a certain decrease in a voltage. After that, whenever we go deeper, it's
Increasing. Voltage.
Yes. If you hit the zero, then you're out of range. It has a distance from 0 to 10 volt it can do. If you go below 0, you're basically out of range, and then you got 10 volts immediately.
Yeah, it is out of.
In the second you hit the 0, you're out of range and you have 10 volt signal.
636. So should
You also have an offset of plus 500,
should I keep 0?
which is okay though.
Huh? I keep
Yeah.
0. I take this one.
So is it working? No? So what might be the problem?
80 millivolts.
Okay, let's see. So, first of all, if you can't find it, it's down here, yeah? And it's at 80 millivolts.
Yeah.
But your range here, I see, is from 9 volt to 2 volt. So your offset is minus 5 volts. Okay? So, okay, you can't see it. It's good. Let's go to maybe to 0. First of all. Now, the signal is still down here because it's at minus 5 volts. Okay? So to get it up from minus 5 volt, I can zoom out. Then I can see it. And now let's try to get it to closer to 0. So I have to decrease the distance. So let's check. close to 0 somewhere. Burp, 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 burp. Let's clear it to get a new measurement. I'm at minus 900, minus 800, minus 600. No, that's too far. 80, 60, clear. Minus 50, clear. I'm trying now to reach minus 200. Because I can show you. Because it's inverted, I guess. Okay, now it's on. Oh. Minus 40. Okay. And now we zoom in to see something. Let's get it to minus, to minus 100. We can manage that. And let's put in an offset of 100. Oh, come on, not that. 100 millivolts. Okay. And now we only probably have to invert. Oh no, not that one. That shouldn't be inverted. I want channel 2. Okay, did something change here? Minus 1. Minus 100 millivolts. Okay, maybe where at we? At 200, okay. We're at 300. So what we need is plus 200 millivolts. Now we should be good. We're at 50, no, why? Is it minus 200 what I need? Probably it's minus 200 what I need. Okay, why is that? That changed a lot now. 300, 200. Okay, like that, clear. Now let's take that. Let's invert it. Now it's at, no! That one. Okay. Okay, and now we have to offset it by, first of all, we have to zoom in a little bit. And now we have to offset it by 200 to get it to 0. It was, sorry, so. Okay, it took a little bit longer than it should, but right now the signal is at shifted to 200, so it's at, which is at the 0 axis, and the other signal is here between
Up and down.
50 millivolt plus minus 50 millivolts. That's not good, because we said we want 100 millihertz is good, 1 volt is good. I see the wrong axis. Yeah, 500 and negative 500. Now that looks good. And now, as soon as somebody does something, you will see, right? So now we should be able to also see the piezoelectric sensor, but 50 is still, that means one of these things has 50 micrometer and the whole thing only shifts by 10 or 40. So I suggest to put that to 20 millivolts. Now only we have to change that again to 200 because that is connected, millivolts. And now we have an even higher magnification of the signal, okay? Okay, and if we put it like that, now you can actually so please all just a step back, and now you can turn on the high voltage amplification. And now let's see what happens. So what do you think? Is that how it should look like? No? Why not? It's a time-based signal. So always you go through 0 and then a little bit higher, and then the polarization changes. And then you go below 0 a little bit deeper, and the polarization changes. So this is actually exactly what we want to see. But now we can hit acquire. And the time-based mode we show now is like this, rolling. And then we can show an XY mode. So what do you think about that? Good? Okay, and then we can hit display, and then we can go to persist, and then we go to infinite, and then it stays. You can see still a little bit of noise, a little bit more of noise. But with a little bit of creativity, you can also identify a butterfly. Okay?
It is not symmetrical.
Why not? What is not symmetrical?
Like
Symmetrical. Emax at the right side is more than the Emax at the left side.
Yeah, maybe a little bit, but I guess it's still an actual experiment, right? It will not be perfect in the end, but it is quite good. And now we need to determine basically this peak and that peak, because that will be the voltage at which the coercive field strength will be. So how we do that? That will be, yeah, we can stop the whole thing. Please turn off the...
Can we use offset to reduce the noise?
An offset?
Because we can set the limit, like we need the values to these this limits one. We don't need it.
Yes, what we would need to reduce the noise is a live bandpass filter. Okay, so anybody of you know what a low pass, a high pass, or a bandpass filter is? No?
About low pass and high pass.
But you know what low pass and high pass is? Yes? Okay, and a bandpass is basically a combination of both. So there you have a band of frequency that you let through. So low pass is quite easy. So imagine you have a tank of water, okay, and you have droplets coming in, and sometimes more droplets come in and sometimes less droplets come in, but you want them to always be the exact same flow. So what you can do is if you put a tank in between, and then you have a certain level, and then over time sometimes more water comes in, sometimes less water comes in, it always stays above the same level. So this is the level it should have, and it always goes like this. But you can open a second valve below and reduce it always, or let out always a constant flow of water. Always constant, but the input is always like this. Okay? So this is a low pass filter. High frequencies. Yeah, I will be there in a second, and then we're done. Basically, some high frequencies that come in are not reflected down there, because there's always constant. But now if you imagine that for a longer time nothing comes in, the tank grows empty. So if you have a low frequency input, it will also reflect down there. So it will, nothing comes in, nothing comes in, nothing comes out, nothing comes out, and so on. But the sudden changes will not be reflected in the output. That's a low pass filter, because high frequencies are filtered out and low frequencies pass. So what you have here is you have some very high frequency. This is the noise, and you want to get rid of that. So you put in that all frequencies above cannot pass. So this thing has either an analog low pass filter that would be a conductor. So for electrical components, a conductor is like a tank. You know that? A conductor can charge, and then you can put something out. So a conductor is an analog version of a low-pass filter, or it has a digital low-pass filter, and it also has an high-pass filter, and then it has a band-pass filter. So high-pass filter is the opposite thing. You only take the sudden changes, and you leave out the medium, low frequencies, whatever. And a band pass is that you say, okay, below this frequency and above this frequency, or the other way around, you don't want anything. So that is vanished then. So this is how. So if you want to get rid of that noise, you need filters. Okay, frequency filters. This is how it will work. But we don't need that right now because you see this is kind of a sharp kink, and we need exactly the lowest part. So we only need to find that. And I guess if you use the cursor, and I'm not quite sure, probably measure, indicator on.
Vertical and
Vertical and
No, don't use that. This is the scale. This could be the one, not sure. So do you need to see the cursor? Probably you can just hit on it. Try to find it out, I'm not sure. Okay, second group, what do you have? Nothing? Sorry?
Nice.
Okay.